Ladies and gentlemen, it's my great pleasure to announce and introduce our next speaker this morning, Professor Brian Schmidt. Brian is one of the most eminent astronomers. He received his PhD in astronomy at Harvard University in 1993, working with Bob Kirshner. And as a young postdoc, still at Harvard, a good year later, he formed the High C Supernova Search Team, which searched for distant supernovae. And this research work led to the discovery of the accelerated expansion of the universe in 1998. A very profound discovery that quite literally changed our understanding of the world and the universe. And this discovery also led to the award of the Nobel Prize to Brian Schmidt, together with Adam Rees and Saul Perlmutter in 2011. I remember this day very well because I was in this building at the time in a lecture hall nearby where we had a conference on dark energy when the Nobel Prize was announced, and the field of dark energy was started by Brian's discovery. So that was very fitting, and of course people were standing up and cheering. Brian has received many other prizes, many more than I can list here. Among the most prominent ones are the Shaw Prize in Astronomy in 2006, the Gruber Prize in Cosmology in 2007, and the Breakthrough Prize in Fundamental Physics just last year. He is a member of many academies, boards, learned societies of all sorts. He is a fellow of the Royal Society in the UK, a member of the Australian Academy of Science, the United States National Academy of Science, and the Spanish Royal Academy of Science. He is also on the board of the Australian Wine Research Institute, illustrating one other passion that he has, among many others. And I think without much further ado, I would now like to give Brian the word and let us give his State of the Universe address to this audience. Thanks a lot.
Thank you, Volker, and it's a great honor to be able to come and address you. As a Nobel Prize winner, being able to hang out with a bunch of the people who have helped make my work possible in the same way that previous physicists have made my work possible. There really are amongst the audience here my heroes as much as hopefully the audience's heroes as well. So I want to give you in about 40 minutes a snapshot of the state of the universe. That's a big ask, so it'll be relatively fast-paced, but I think you'll get a good sense of where we are. So I'm going to lead out with the answer straight up front. And that answer is that the universe is expanding. The universe is 13.8 billion years old. That's about 10 to the 18 seconds if you are into that unit. We are very close, as I'll show you, to geometrically flat. That is, that the universe does not have any discernible curvature. And the universe is made up of a very funny mix of things. It's roughly 69% this stuff we call dark energy. You'll understand more what that is, but not completely. Dark matter, 26%. Atoms, about 5%, of which 74% is hydrogen, and most of the rest is helium. Neutrinos make up about 1 part in 1,000 of the universe. Photons, even less, 1 part in 10 to the 5. Now, that is quite changed from even 25 years ago, where we didn't know things to factors of 2. I think 10 orders of magnitude is a little brutal, but there are things we are out by that much. But ultimately, astronomers and physicists are out to take ideas and test those ideas through measurement. And in that sense, Plato really is a dark cave of confusion to an astronomer, of which you try to get away from as fast as you can. Everything we do is based really on measurement, and to the level you can measure something, you believe it. To the level you can't, you don't. And that is sort of what separates I would say pure theory, or even metaphysics if you can't measure it, from the physics and astrophysics that me and my colleagues tend to do. So, let's go right back to the beginning of cosmology, the study of the universe itself. Edwin Hubble, 1929, had access to the largest telescope in the world of that day, the 100-inch Hooker reflector just outside of Los Angeles on Mount Wilson. And in 1929, he showed this diagram, the Hubble diagram as we now know it. And what he did is he looked at stars in galaxies, and he judged the relative distances by how bright those stars are. The further the star, the fainter the star. And then he measured what he thought was a velocity by the Doppler shift. He would look at its light, and if the light were stretched, then that stretching of light would indicate a velocity. And you see that almost all the galaxies were moving away from us, something Vesto Slipher had discovered, and that there is a correlation. The further the object, that is the fainter the stars, the faster the recession away. And from this he announced that it meant that the universe might be expanding. And to understand that, I'm just going to give you a visualization that if you have the universe and you expand it, so I've expanded it there, and you overlay before and after, what do you see? You see a universe in which the nearby objects have moved a little bit when I expanded the universe, and the distant objects, well, they've moved a lot. So you can kind of expect that a universe that's expanding, at least in this two-dimensional representation, to have this thing that Hubble saw. The further away, the bigger the motion away, or the greater the expansion of space. So if the universe really is expanding, we can think, well, what happens in the past? So we run the universe in reverse, and as we look back in time, we expect things to be closer and closer, and there will be a time when everything in the universe is on top of everything else, the thing we call the Big Bang. That's sort of a natural expectation of an expanding universe, that there will be a special time in the past. And in order to avoid that, you have to invent something like matter being created, or something in a line of what the steady state universe was back in the 1960s. So if we have this Big Bang, people always say, well, what came before the Big Bang? Well, I don't even know what the Big Bang was. As an astronomer, I only know what happened after the Big Bang. And that time after the Big Bang is the time of rapid expansion. It is a time when we can see the universe acting as a giant nuclear reactor. Time of 1 second, it had a temperature of roughly 10 to the 10 degrees and a density much less than the center of the sun, but the same equations of nuclear reactions work, and you can calculate that the universe should have produced about 75% hydrogen in those reactions from fairly first principles. The last real observation we have, besides that ratio of nuclear energy, the nuclear production of elements at about 1 to 1,000 seconds, is this picture. This picture is known as the cosmic microwave background. It is an image of the universe when it's 380,000 years old. Its temperature is roughly 3,000 degrees centigrade. And that's an important time because that is the temperature where hydrogen is able to hold on to its electron. And when hydrogen combines with its electron, it suddenly becomes a much smaller target for photons. So photons before this time were bouncing from hydrogen atom, or from electron to electron, scattering, creating a fog that you can't see through. At this time, very quickly, the universe went from being opaque to transparent as the electrons were grabbed by the hydrogen atoms. And so suddenly we sort of have this wall where we can see no further, but you can measure this and you see there is a pattern, and we'll talk about that later on. That pattern turns out to be sound waves left over from the Big Bang, very big sound waves, and that pattern, distinct as it is actually smooth to 1 part in 100,000. So that image there is smoother than a billiard ball, but still has a little undulating pattern in it at about 1 part in 100,000. That allows us to very precisely probe physics and our model of physics back at this time. All right, so what does Hubble's observations suggest we should be thinking about when we look at distances in the universe? Well, Hubble says the universe is expanding, and if it's just doing it and not changing over time, then you could imagine you run the universe back in time and you get the age of the universe. That is, Hubble's constant, the rate that the universe expands, tells you the age of the universe to first order. Of course, life's a little complicated because the universe might have stuff in it that causes you to think that the expansion rate of the universe will change. Now, measuring the age and expansion rate of the universe as the Hubble constant is something I did for my PhD thesis. And here I am in 1993, very excitingly showing my PhD supervisor the answer. And the answer I got back in 1993 when I finished was that the universe was roughly 14 billion years old. And the Hubble constant, measured in astronomers' units, is 70 kilometers per second per megaparsec. And a megaparsec is a unit which I won't explain to you, but it's roughly, 3 million light years. So if a galaxy is 3 million light years away, and on average it will have a recession velocity of 70 kilometers per second. And that, if you take the reciprocal of that, it's roughly 10 to the 18 seconds, or 14 billion years. Now, as I indicated, we have some physics going on, and that physics, general relativity, gives us the physics of gravity. And Einstein is an interesting person, and his motivation for the theory of general relativity came from watching someone fall off a roof. Now, normally, if I saw someone fall off a roof, I would run possibly for their aid and get an ambulance or something. But Einstein's moment, not unlike Newton's apple, was, wow, I think that person doesn't feel gravity when they're falling. And I think that must always be true. What does that mean? Well, that was his thought in 1907, that acceleration due to gravity and acceleration due to motion, to accelerating motion or speed, are always equivalent. And so if you go through and you're in a rocket or you're in a box on Earth, you literally cannot tell the difference between acceleration, going faster and faster, or being accelerated by gravity. It took him 8 years to reconcile that, and in 1915, in November, he published his theory of general relativity. Since we have a lot of mathematicians, you should know that Hilbert published the field equations 4 days before Einstein did. Okay, why? Well, because Einstein was not as good a mathematician as Hilbert, and he was asking for help with his homework. And he was corresponding with Hilbert, and Hilbert figured out the solution quicker than Einstein did. Although I think Hilbert did give correction to... Very important exchange, but one most people are unaware of. So good, and it's good to have someone who's actually been there and had the chance to understand at least a bit of it. All right, so it turns out general relativity is the thing that really made Einstein famous within the realms of the public. That was not E equals mc squared, but rather general relativity, being able to come up with this idea that predicted that space would be curved and that you could go out in an eclipse and see that stars were displaced from where predicted. That was the thing that really made him a household name. The work that led up to Hubble turned out to be work that was predated in many respects. Alexander Friedmann went through and thought through as imagine an infinite universe, or a universe that was very large, of constant density. What happens with Einstein's equations of general relativity? Came up with the first solutions. Those were recreated by Lamont in 1927 in his PhD thesis, which he showed at a conference to Einstein, and he predicted that the universe should effectively be expanding, and showed that some data from Slipher and Hubble seemed to confirm it. And Einstein, unfortunately, told Lamont that Friedman here had already done the mathematics, and that while his mathematics was impeccable, his physics was abominable. And so Lamont really did figure out that the universe was expanding in his PhD thesis, but we give Hubble the credit because Hubble was bypassed Einstein and went straight to the New York Times. Probably a brave thing. So the standard model coming essentially out of Friedman is one where you take the 10 coupled partial differential equations, which are general relativity, and by assuming that the universe is homogeneous and isotropic, you can boil them down to a single ordinary differential equation that even an astronomer can solve relatively straightforwardly. And so this equation has a few components. It has this thing called A, the scale factor, which is how big a piece of space is over time. And we usually give it a ratio to the current epoch, A0. So that's one. And it turns out you can measure that exquisitely accurately to the redshift. That is, the light of objects gets transformed or stretched by the scale factor as it travels through space. And we can measure this to 1 part in a million, or even probably 10 million if we need to. So we can measure that very accurately. We also have here the curvature, and in general relativity, that can have 3 values: open, closed, or flat. You have the density here, and then constants. And if you're a true theorist, you always set all the constants to 1 and move on. But for an astronomer, that always seems a little confusing to us. So in the parlance of astronomers, we have the Hubble parameter, not a constant. It's a parameter. It changes. It's essentially the relative derivative, time derivative of the scale factor. That's how fast the universe is expanding now. And the value of that is a unit, as I said, is around 1 over about 14 billion years, 1 over 14 billion years. We have the notion of that critical density where the universe's geometry changes from being open, hyperbolic, to closed. And that you can calculate as essentially the Hubble constant squared divided by the couple other constants. And that has a value of about 9 times 10 to the minus 27 kilograms per meter cubed. So it's a very small number when you think that Earth's density here is 5,500 kilograms per meter cubed, or 30 orders of magnitude less. But as I will show you, it turns out the density of the universe is very close to that. And we call that density usually the ratio of the real density of the universe to this critical density, and we give that parameter omega. All right, so the density, it turns out, can be the form of anything. Anything that has matter or energy, or you can convert to energy. So atoms, photons, neutrinos, cosmological constant, or something else, strings, whatever. Anything that has matter or energy is part of a contributor to that density that sets the critical density and the geometry of space. So if you solve that equation, you get a lot of solutions. You can have a universe that's just empty and it keeps on getting bigger over time. You can have a universe that has density less than the critical density. That's a universe that slows down monotonically over time, but does not completely stop. It keeps on slowing down, but keeps getting bigger over time. Then you could have a universe that has greater than the critical density, such as closed geometry, so the volume of space is finite if the universe has greater than the critical density, and the time history of the universe is also finite. So it's a universe that has a beginning, and as we like to say, has an end. The Big Bang and backward, the Gnab-Gib happens sometime in the future. Finally, you have a universe that might have the cosmological constant, which we'll talk about later. Now let's talk a little bit about how geometry is related to this density. As I said, a universe that's flat, well, triangles add up to 180 degrees. A finite universe has this closed geometry, triangles more than 180, and open less than 180. And so that space, which is of course 3 dimensions of space and 1 dimension of time, is something that's going to affect how we observe things in the distant parts of the universe. And I'll show you how we can actually go out and make measurements now, especially with the cosmic microwave background around that. All right. So the idea in 1994 that was made possible by technology and by some new ideas about how to measure distances more accurately was to go through and measure the universe's past. So if you go back and look in time at nearby objects, you're looking maybe 50, 100 million years in the past. And if I look at objects that are billions of light years in distance, I'm looking, of course, billions of years into the past. So imagine that I measure distance in redshift to nearby objects and compare that to distance in redshift of distant objects. I'm looking at the expansion rate of the universe back in time. And that's an integrated effect, but I'm going to ignore that right now. And so if the universe is, for example, expanding the same rate back in time, then this line will be straight in this diagram. On the other hand, there's that critical line between whether or not the universe expands forever and has less than the critical density or stops expanding in the future, goes in reverse. And so that critical line, it looks like something like that dotted line in this diagram. All right. And so if your data in the past is below that dotted line, you know the universe is finite. Above it, the universe is infinite. How are we going to do that? Well, as I said, we needed a set of objects that allowed us to look back in time. And those objects were type 1a supernovae. What's a type 1a supernova? Well, this is one scenario. It may or may not be the correct one. But effectively, if you take the sun and put it in a binary system, then as the sun starts to run out of nuclear fuel, it will puff up, and if it were next to another star, it would donate its outer envelopes to its companion star. That other star will be hot, and it turns out when stars do this, they become what we call planetary nebulae, which are quite pretty objects to look in the sky. Meanwhile, back in the center of this system, that second star, which has got all this extra material, its nuclear generator will be heating up, getting more powerful. It will puff up and be able to donate some energy to that, or mass to that white dwarf. And when it does so, it will make it, under certain circumstances, grow in mass until it reaches this particular mass of 1.383 times the mass of our sun, the Chandrasekhar mass, as we call it, where the star will become unstable. Now, in detail, it becomes unstable to gravity, effectively. And in detail, just before it gets there, the center of the star will ignite and start burning, and that burning will run away, and you end up with an exponential runaway where the whole thing ends up igniting and burning in a period of a second, 1.4 solar masses worth of nuclear fuel. That produces a very bright object, a type 1a supernova. They take about 20 days to reach their maximum brightness, which is 5 billion times brighter than our sun. And then they fade away. In the process, they make 2/3 of the iron that we all are sitting on in these chairs, for example, in that steel. All right. So to understand how to measure these things, a group in Chile came along at what we call the Colón Tololo supernova search. And they went out and did digital measurements to about the 1% measure level to go out and understand how you can precisely use these to measure distances. Because they're not all exactly the same, but there is a way of calibrating that. That was done in 1994, and that formed one of the foundations, along with new telescopes, 10-meter telescopes. And so on my way to Australia, I sat in this office and worked with Nick Sunsteff up there. Pete Chalice was around as well. And we talked about getting along and doing this experiment that had been thought about conceptually for 50 years plus, but that it was possible to do it. And the thing that enabled us to do it was, as I said, the telescopes and the computers of the day. Now, the computers of the day in 1994, I think we use Pentium 200s. They weren't anything too flash, but they were better than what came before them. And we would take, with the new digital detectors, in which case we would take roughly, initially, about 1,000 2K by 2K images in a night, and we have to analyze it very quickly, about 12 to 18 hours. And in those, there would be thousands of galaxies, and the key was to find, in that roughly 50 gigabytes of data we would take at a night, the 4 things that changed in all that data. So it was early and very crude big data science, and so I used many of the techniques that we'll be hearing about in this room to try to do that, and I can tell you modern AI is a lot better than the stuff in 1994 in terms of how it actually works. So the deal is to find essentially that little thing, and we do that by taking 2 images separated by a couple weeks and looking at nothing becoming something. So that is a supernova 5 billion light years in distance. It exploded before the Earth was formed. And so you do that many times. As I said, in that 50 gigabytes of data, there'd be 4 of those. Now, to give you a sense of how this was really done, I take you to Chile on one of our observing runs. Here we are at the Sotillo 4-meter telescope that was equipped with the largest digital imaging camera at the time. And we would go through, and we only get 6 nights a year, so you want everything to work well. I don't have a supercomputer. I've got 50 suns is what we had back in the time, and I tried to link them together with a bunch of messy software. And so my job was chief programmer, and the data would come in, we'd be making sure everything was fine, and then my software would do its best to throw up candidates as best it could, and then we used the really good neural networks, which was a team of about 15 people going through and looking at all the junk my software put out and finding the last 4 or 5 things that might be good. And as I said, we had to do that all in about 12 to 18 hours. Because after we found something, we had to get more data on it, and we didn't have the ability to take data on everything. And so after 18 hours, we would send the finding charts over to Keck, the largest telescope in the world, the 10-meter that had just been commissioned in 1994, and there Adam Rees, for example, and Alex Filippenko would be taking data to get the redshift and to confirm it really was a Type 1a supernova, and voila, we had a measurement. So we did that for about 3.5 years, and after 3.5 years, we started looking at our data, and I can never forget the day that Adam sent me a figure and said, "What do you think about this?" Question mark. Just to let you know, we used to have to, if you recall, there weren't attachments back in 1997, so you would take your figures, you would UU encode them, and do all these things that I think most of us have forgotten about. And they would take forever to get to Australia. And this is what the data looked like. And I remember writing back to Adam and saying, we seem to have made a mistake. And the reason I said that is because each supernova here is a measurement of the expansion rate. And when I compared the nearby ones to the distant ones, there was something wrong, which is that these objects lie in the part of the diagram where gravity was not slowing the universe down at all. Rather, when we did the analysis in the end, you were sort of 99.9% sure that it lie up on the top of the diagram where the universe was accelerating. And that was not something that I thought was a reasonable possibility in 1998. And so after 6 months of hard work and checking our results, we eventually published a paper after we could not figure out any way that we could have made a mistake. Turned out at the same time, Saul Perlmutter, who was a competing team to us, was getting the exact same result, and so 2 teams published this crazy result in the same year, 1998. And so here are the 2 papers, and just so people remember that there are teams that do this, our team and Saul's team in Stockholm in 2011. All right, so this was a surprising result. The universe is accelerating. Why? Well, Einstein actually thought of that in 1917, probably by accident. He had this idea of energy as being part of space. He just called it the cosmological constant. And if that stuff exists, energy that is thinly distributed as a property of space, it doesn't clump, then the equations of general relativity say that stuff has negative pressure and will cause gravity to push rather than pull. Now, generically, we call this dark energy now, so it turns out it doesn't have to be a property of space that's immutable. It can change, and there are different ways in particle physics to do that. So a generic way of describing it is this stuff that is called dark energy. So the detailed analysis of our work was that the universe is a mix of about 30% matter that pulls, so normal material, and 70% material which pushes, stuff that has negative pressure and causes gravity to push. And that was sort of the mixture that we needed to make our result make sense. So that means on this diagram we have to add another possibility, which is stuff where the universe slows down, becomes less and less dense. This material has a constant density, so it's becoming a larger and larger fraction of the universe until about 6 billion years ago it becomes the dominant constituent of the universe. It then causes the universe to then start on a period of what we assume is unstoppable exponential expansion. Although, as an astronomer, I will warn you against extrapolation, unless you think your theory is perfect, which we always assume it's not. All right, so how else can you go out and look at this problem? One way is to go out and measure the distribution of galaxies across the sky. And here's an experiment that Australia did with the United Kingdom, something called the Anglo-Australian Telescope Survey, AAT. And you can see the galaxy across the sky create sort of this foam-like structure. And the way we can understand that is through equations, but also computer simulations. And so computer simulations, Volker Springer, the chair, is someone who has pioneered doing giant simulations of the universe, 10 to the 10 particles now. And you start with sort of a distribution, then you let gravity bring them in, and in the very center bits, it's very highly nonlinear, but you put all the laws of physics that you can in there, and you see what you get. And you get these very complex, rich structures, which then you can compare to what the universe really looks like. And to first order, the density of how much stuff there is in the universe really sets what you expect to see. And so here is an example of how you might have done this in 2001. You have the universe you really have, and then you have computerized versions of that universe. And your eyes are pretty good at doing the analysis. You have little, I think, power spectrum analyzers in our brains. And so you can go up there and say, is it 1, 2, 3, or 4 that most looks like the data? And it turns out if you said model 3 with your brain, you got it about right. And that model was one of which had roughly 30% of the amount of matter to make the universe flat. So cosmology in your head, I think by eye, is the same thing that the sophisticated analysis gave. This experiment really is insensitive to dark energy. It only measures how much matter there is in the universe of normal attractive material. And so the measurement's pretty clear, but that turned out to be about 6 times more gravity that pulls than can be explained by the number of atoms we can actually go out and account for in galaxies and gas and everything in between. And so that brings up the next problem, which is the stuff we call dark matter, the material that always seems to have gravity, but we can never directly account for. And everywhere we look in the universe, we see this dark matter. We see it as galaxies rotate. They always rotate faster than they should. And the idea is that it may be some undiscovered particle, like a neutrino, that weakly interacts, hopefully it weakly interacts, and goes right through the Earth, right through most things. And so it has gravity, it interacts via gravity, but it doesn't interact through any of the other forces of nature, and so it's really hard to see. You can put that stuff in these giant simulations, and it turns out you need to have it there to show the answers that we get. And no matter where you look in the universe and clusters as they pass through, you see evidence of this dark matter. So one of the places you can really test that theory of dark matter is in the cosmic microwave background. I've told you these are sound waves left over from the Big Bang. And so you're seeing tiny little ripples of matter. And so since we are in a mathematical object, this is essentially what we think is a Gaussian random field, and you can go through and let it propagate. It's in the linear regime, so very nicely it remains a Gaussian random field, and you can go through and play lots of tricks mathematically on this to analyze it in detail. And from a physical point of view, what the pond is made out of, the universe is made out of, affects the wave action. It's how material interacts with itself. And so the Big Bang, we think, created, through quantum fluctuations, it seems, the perturbations, which were the initial seeds of the sound waves. Those sound waves propagate out, and then 380,000 years later, we get a snapshot of how those sound waves have propagated. And it depends critically on what the universe is made out of. And so, just to show you what the theory gives, you get a series of modes of different lengths, of different amplitudes, depending on how much matter there is, baryons, so those are atoms, how much dark matter relative to those atoms there are. It gives you a different set of curves, and that is what we actually measure. Now, I want you to think, if you are a skeptic about dark matter existing, or the standard model existing, this curve that fits this was developed before the measurement was made by several years. We went out, we measure, and you get a curve that fits the data that is very, very complicated with lots of degrees of freedom, exactly within the experimental errors to a high degree. You get rid of dark matter, it doesn't fit. Turns out if you get rid of dark energy, it doesn't fit either, but that's for a different reason, just the geometry of space I'll show you in a second. But the fact that you're able to predict that tells you that you think you know what's going on, even if incorrectly, but you have a fundamental basis of predicting reality as we see it. That tells you very precisely that the ratio of a component of material that has normal gravity but does not interact in any way is 6.5 times more dominant than atoms that have normal pressure, like the stuff in this room. And that is a very precise measurement. It turns out you can also, by looking at how big those sound waves are, the sound waves travel at the speed of sound, which is very conveniently 57% of the speed of light, times the age of the universe, you can predict how big those sound waves will look. And since space ends up as magnifying or demagnifying light, depending on its curvature, then you are able to make a measurement of the geometry of the universe. And it turns out this is, again, shows up, if the universe is curved, things just get magnified or demagnified. Dark energy, which accelerates stuff at the very end, is a small component of that. But the measurements are so accurate, it turns out now, you can measure with extreme accuracy that the universe is geometrically almost exactly flat to within roughly 0.5% averaged over with all the other confounding variables. So that is an amazing place to be in 2016 when you think in 1991, I bet my office mate that we would not have this measured to 1 part in 3 by this year. I lost that bet. But it's all right. I don't mind losing bets in that way. All right. So we have a universe which all matter adds up to 100%. It's almost exactly flat. 30% of that stuff has normal gravity. That's from the galaxy and the sound waves. And that leaves us that you have to have a universe which is 70% mystery matter, and it all works that this stuff causes the universe to accelerate, that the part of the 70% that's missing that you need, no matter how you look at the universe, you see you need to have this dark energy some way. And so we have a very messy universe, a universe which isn't just made out of one thing. It's actually made out of at least 3 and even worse 4 things, because neutrinos are there as well, all within 5 orders of magnitude of each other. And photons are there as well. Why? Well, some people believe coincidence like that should not happen, but no one has really come up with a reason at this point why it's not a coincidence. So, the density of the universe is measured very accurately to within a few percent now. and those are the numbers. The photon density is measured very accurately as well because we can measure the cosmic microwave background, and those photons are what fill the universe, and the value, as you can see, is about 10 to the minus 4, 10 to the minus 5 of the critical density. We can measure from cosmology the neutrino density. Why? Because neutrinos change from being sort of interacting to non-interacting, from being relativistic to non-relativistic. And they can, because they don't interact in the later parts of the universe, they can pull on the rest of the material and essentially smear out the structuring, the clustering. And so if you have heavy neutrinos, the structures get blurred compared to having light neutrinos. And so you can actually go through with the theory in place quite remarkable limits now on the mass of the neutrinos, which are bounded by essentially particle physics as measured from neutrino flavor oscillations here on Earth at this level, and this is sort of the cosmological bounds right now, and that corresponds to this set of densities of these things in our universe. So we can do a little bit better on those measurements of cosmic structure, and maybe one of these days we'll actually figure out what the mass of the neutrino is this way, or maybe we'll make a measurement here on Earth. We have two ways to get through that. So the cosmological model, as you see, is at some point really nice because it can predict things so well, but it's got some ingredients that we have to sort of make up. So the idea is you start with the initial fluctuations, which are caused in the standard model because small parts of the universe exponentially expanded and took things from the subatomic scale, quantum scale, to the size of the universe's horizon. And when you do that, you keep on getting quantum fluctuations exponentially expanded, and so you get essentially a white Gaussian noise perturbation spectrum. And it turns out, when you go out and look, that's what we seem to see. Now, it's a relatively generic prediction, and you need to have inflation to do it. So inflation is something that's sort of a cartoon, but not really something that's easy to test directly right now. You have photons, neutrinos, baryons. Those are all good things because we see them on Earth. Then we have this dark matter stuff that might be a particle we can discover, but we haven't discovered it yet. We have dark energy that we just sort of barely know it's there. The only way we can tell it exists is by looking at how it affects the universe on the largest scales. But no matter how we do it, we do see evidence of that at this point. The universe is very homogeneous. We see it's the same density and temperature to 1 part in 10 to the 5 when we look in all the different directions. We are, of course, assuming general relativity is effectively exactly correct in this regime. And this essentially agrees with every measurement we can do. There's one piece of tension, is that if you go through and you measure how fast the universe is expanding by looking at the cosmic microwave background, so that's taking a fit of the universe when it's 380,000 years old and extrapolating it to the current day, and then you just measure it directly, and my colleague Adam Rees has done this, there is roughly 5% tension between those measurements, which on face value you would believe is a 3 sigma discrepancy. Now, I'm not sure it really is 3 sigma, but it is an interesting tension that is certainly worthwhile looking at in detail. And indeed, I have a student looking at it in detail. But otherwise, everything sort of holds together, except for you have to make up 3 things. But that's physics. Physics is about making assumptions, right? And those assumptions are effectively these 3 things, but they too make predictions. So the big questions: what's dark matter? What's dark energy? Why do neutrinos have mass? The theory, the standard model of particle physics, says neutrinos should not have mass. They do. So something's missing there in that underlying theory. The theory also has symmetric equations so that when you have a hot universe full of photons, you should end up with no atoms, no particles, because all the equations are exactly symmetric. Everything cancels out. So you should not have atoms. We should just have a universe full of photons. So there's something missing there, the fact that we exist at all. And finally, we have this idea of what is inflation? Why did the universe exponentially expand when it was young? Or do something similar to that, and why did it stop? That is a cartoon theory. But, of course, the universe is not just cosmology. Astronomy is full of some surprises. And this year, or last year, in September, we had a surprise where the gravitational waves were looked at, and it's worthwhile just understanding that using computer simulation, general relativity equations, where you put the merger of two black holes that have rotation and essentially curved black holes, they were able to pre-predict the signal that we actually saw within the experimental errors. Now, if you had asked me, would the chirp, that is the gravitational wave signal, at that level really exactly look like the theory in advance, I would have probably said unlikely, because we know general relativity must fail at the quantum level somewhere, and you're right on the horizon. If it's going to fail, it's going to fail there. Well, unfortunately, I would say it hasn't. So we are going to get thousands of objects like this over the coming decades, and maybe statistically we will be able to see that there's some deviations of general relativity. But at this point, we haven't. So it's going to be an exciting time for this part of the theory meeting observations over the next 10 or 20 years. So this is just the beginning, and I think it's worthwhile highlighting this as one of the major results of the new millennium. There is some hope that we can get and test inflation. This is a U.S. installation down at the South Pole, and there was a false start of a claim of seeing gravitational waves left over from the inflationary epoch, where those quantum fluctuations being expanded create gravitational waves of space that perturb the cosmic microwave background enough that you can actually measure it through polarization. And you see it as a curl signature within the polarization of the cosmic microwave background, and you can see it sort of represented there. Very exciting. When I saw this, I was a little worried about dust, as everyone else was, and it turns out this is a map from Planck, the European satellite of the dust, and they've been able to measure the polarization, and it turns out there is no nice, clean part of the sky, and unfortunately that BICEP 2 measurement, is consistent with the dust signature, which can also have a curl to it. But the measurements are getting much better, and it may well be that they will be able to tease out a measurement of the gravitational waves left over from the inflationary epoch, in which case you could actually test inflation, something that happened when the universe was less than 10 to the minus 30 seconds old, at a place where gravity and the other forces of nature are likely coupled. That would be exciting, and it would be essentially an indirect proof that gravity is quantized, because the fluctuations you see really do arise from the quantization of gravity. So that was a false start, but as Albert Einstein said, and he said many things, if we knew what it was that we were doing, it wouldn't be called research, would it? And so I always remind people we need to celebrate our mistakes as well as our successes. So thank you very much.
Will be questions, and if you please would stand up, that would help our cameraman to put you up on the screen as well.
Hi, thanks a lot for the very intriguing and educative talk. My question to you is about your take on the simulation hypothesis.
Tell me your version of what you think the simulation hypothesis is.
To put it in a nutshell, as far as I understand it, and by no means am I well informed, is whether or not the universe that we live in and everything we know of it is simulation.
Okay, so it turns out one of the philosophers who works on this used to be at my university, and I would say one of the beautiful things of hanging out with philosophers is I feel much less wiser, hence why Plato causes me problems. I think he has convinced me that there is no sensible way for me to demonstrate we are not in a sufficiently complex simulation. I take it, therefore, as being it is not beyond the possibility, but I figure if I'm part of that simulation, my job is to go out and measure the simulation, so that doesn't bother me. So.
Magnificent talk. There's so many questions, I don't know where to begin, but let me just say, I was a bit surprised that the word black hole did not figure in your lecture.
Yes, so I did feature it at the very end in the gravitational wave measurement, and so I think, I was always, we always talked about, well, how do you go through and test things? Well, black holes have always been complicated because we see things on scales thousands of times larger than the horizon, But when you look at that merger of two black holes, and that chirp that they fit is a merger of two approximately 30 solar mass black holes, of where you need to worry about the fact that they have angular momentum. And you can go through and wind it up and you see exactly what we saw. I would argue that's seeing a black hole. We have probed very close to the horizon, and until we, I think it's going to be hard to do a lot better than that. But the way we will do better is by looking at thousands of systems and root-inning our way down in the noise and seeing if there is something that isn't quite right. Short of seeing Hawking radiation directly, which I'm not terribly optimistic about in my lifetime, or the shadowing. So there's a big program here in Europe where with the very long baseline interferometry, we can actually look at the black hole in the center of our galaxy and look at stuff behind it and essentially see the shadowing on that potentially. Those are two other ways that we might get in there. But I mean, from my perspective, quite an exciting time. But as a cosmologist, I try not to worry too much about black holes because they are sort of by necessity relatively small and are perturbations of what I do that I don't worry about. So the evidence is that almost every galaxy has a black hole in its center. That's a mystery why there would be black holes that big in every one. One of the exciting things for me is that first system was essentially two 30 solar mass black holes. There was no evidence from astronomy that there were black holes that big. I think there was some indirect evidence, of which at least I thought there was. But it would appear that maybe the first generations of stars made big seeds, maybe bigger than we realized. And with the James Webb Space Telescope, we are going to be able to go back and look. And if there really are 100,000 solar mass black stars, which I'm dubious, but if they exist, we should be able to see them directly. So, let's let the data talk and see what happens.
A further urgent question. I think we are really late. If I don't see any, then
there's
let's think. There's one at the bottom. At the back.
I'll answer it quickly.
Yeah. This expansion of the universe, does it happen on all scales? So is this room expanding too now?
So the answer was, in the early universe, yes, but now no. And within each part of the universe, you can think of a sphere. Just think of a sphere, and then if the density inside that sphere exceeds the critical density, of which this room certainly does, then that part of the universe will collapse eventually. And so it turns out that this part of the universe was expanding right after the Big Bang, but it went on a little cycle, an expansion, stopped, going in reverse, collapsed down to for the Milky Way. And so the expansion only happens between areas that are essentially have less than that the density necessary to collapse, if that makes sense. So those spheres, in our case, we think there's probably an order of 20 to 100 galaxies which will eventually collapse to form a giant galaxy we're part of. But in the long term, every other part does that.
Let's thank Brian again, please.